Hello everyone, welcome to RASAYAN Academy. My name is JAGRITI SHARMA and I'm an educator on the Unacademy Plus platform. So guys, in this video, we are going to continue our discussion on the CSIR UGC NET December 2019 exam question for chemical sciences. So let's begin very quickly and let's see the first question for today. So this is the first question that I have taken from the CSIR 2019 December paper. Alright. And what do we see in the question? The question is a match the following. So match the following for column 1 with those of column 2. So if you look at the options over here, so guys, I would suggest you to stop the video and try to answer this question by yourself. Alright. So if we look over here, option number A is sodium hydride, then it is beryllium hydride, then it is hafnium hydride, and lastly it is technetium hydride. So basically all of these are hydrides of different element. Okay, so what we have to do is we just have to characterize what are their properties. Okay, so first of all, let me also tell you that guys, I have also made a series of classes on main group elements and all of them are free. Okay, main group elements special classes. So if you want, you can visit the Unacademy profile, because these are all free classes on complete main group elements. Okay, so let's talk about sodium hydride first of all. So guys, this is the first group of the periodic table. Alright, so this is the first group of the periodic table, the S block elements, alkali metals basically. So the alkali metal hydrides, if they form hydrides, they are definitely ionic in nature. We know that they are ionic in nature. For example, if you are talking about sodium hydride, it is going to be Na plus and H minus. So the ionic hydride is also called saline hydrides. Saline hydride because of the salt-like nature, Na plus, and for example the Na plus and Cl minus is a salt. So this is similar salt-like nature it is depicting, that is why it is also called saline hydride. So we can say A goes for 4. Now about option number B, this is a beryllium hydride. So guys, we know this, or if you have studied a little bit about the main group elements, you would know that beryllium hydride, again, if we just write BeH2, then it is very clear that beryllium is electron deficient in nature, right? And it is also small. So the beryllium hydride has a good enough covalent character, and what it does is it forms a polymeric chain. Alright, it forms a polymeric chain like this, having the 3 center 2 electron bonds. Alright. Okay, so it is going to be a polymeric chain like this, and these are going to be the 3 center 2 electron bonds, or the banana bond we also call it, just like in the diborane. Okay, so with the 3 center 2 electron bonds, it is going to form a polymeric chain, the beryllium hydride. So this is this question is purely based on your knowledge, what you already know about these hydrides. Okay. So let's now also talk about the remaining two, option number C and D. A goes for 4 and B goes for 1. Alright, let us also talk about hafnium hydride. Alright guys, so basically it's the transition metal hydride that we are having over here. So the transition metal hydride, hydrides are non-stoichiometric in nature. They are non-stoichiometric in nature, and that is why there is a 2.1 over here. So for example, it was if it was stoichiometric, either it would be 2 or it would be 3, but it is 2.10. So definitely this is non-stoichiometric, and that is why if you know a little bit about the non-stoichiometric hydrides, or for example borides, because all of these are small atoms, right? Carbides and nitrides, right? So from the transition metal elements, this is a very common thing which is asked. See, all of these are small elements, and if we want to make the hydride or the boride, carbide or nitride, it is always going to be non-stoichiometric, because it is going to, these atoms, these small atoms are going to fix into the, they are going to fix into the voids like this, and that is why they make the non-stoichiometric hydride. Okay, so इसे हम also we call it interstitial hydrides. Okay, because these small atoms get into the interstices, which is the voids or the spaces between the atoms like this. So it is the interstitial non-stoichiometric hydride for the transition metal element. Okay, similarly, let us now talk about the final technetium hydride. So guys, now the only one option is left, although this is the only one option which is left, option number 3. Okay, tri-capped trigonal prismatic. So first of all, what is a trigonal prismatic structure? Let us draw that. It's very simple. It's the trigonal prism that we talk about. Okay, so for example, I am just drawing roughly a trigonal prism like this. So how many vertices are there? It is 1, 2, 3, 4, 5 and 6. So it is having 6 possible places for the ligands, just like in the octahedral structure. But here it is asking about tri-capped. What do you mean by capped? So one of the faces, for example this face, is going to be capped like this. So this is monocapped trigonal prismatic. This is di-capped trigonal prismatic. Okay, and if we talk about tri-capped, then let's make one more cap like this over here, and now it is tri-capped trigonal prismatic. Okay, and then how many ligands can we see? 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, so now it is justified, the 9 hydrides which can be placed around technetium in the tri-capped trigonal prismatic structure, and definitely this is it. So the correct answer is option number 3, A 4, B is 1, C is 2 and D is 3. So this is the correct answer for the match the following. So this was our first question. Let's now move on to another question, which is asking about the rate determining step in the catalytic synthesis of acetic acid by Monsanto process is. So this is also a very easy reaction, guys. What you have to know is, you just have to know what is the Monsanto acetic acid process, and it is asking about the rate determining step. So this is how the Monsanto acetic acid process looks like. I am just giving you a rough idea, roughly writing the mechanism for you. Alright, so there is how the oxidative addition takes place of the methyl iodide, right? And after the oxidative addition, we get something like this, CH3. This is our CO, another carbonyl, and this adds over here in the SN2 manner. Alright, so after the oxidative addition, we are going to see migratory insertion of the carbonyl into the rhodium and methyl bond, just like this. Okay, and the rest of the molecule remains the same. So there is going to be one iodine like this and this carbonyl right over here, right? And after this, what happens is there is an exchange, or there is an addition of carbonyl group, and we can say it, because the complex was coordinatively unsaturated, it can still take a carbonyl group like this. And after this step, there is directly the reductive elimination step. Alright, so in the reductive elimination, what is going to get removed? The acyl group along with the halogen, which is the iodide that we are having. So I can just directly write it like this, that it is going to give us back our complex, which was like this. For example, let's say, so drawing the carbonyl like this, minus over here, plus the CH3, C double bond O and I. So this is how the acyl iodide has formed, and after hydrolysis it is going to give us the acetic acid. So this is the whole Monsanto acetic acid process. Alright, now the thing is, the question is not asking you everything like this. The question is simply asking you what is the rate determining step. Alright, so guys, how do we know which is the rate determining? Definitely the slowest step is going to be the rate determining step, and the slowest step in the organometallic reaction most of the time is the oxidative addition reaction. So guys, you can see that I've also drawn an energy profile diagram for the overall reaction only for the two steps. So basically the first step, which is the oxidative addition step, is having the highest activation energy, and that is why it is the slowest step. So this is our complex, okay, rhodium complex over here, and if it takes up the methyl iodide plus methyl iodide, this is the oxidative addition, and it forms this octahedral complex like this one. Okay, and after that there was migratory insertion right over here. So the migratory insertion is going to give us this product. Okay, so this energy profile diagram, this place is for this product right over here. Okay, so as you can see that the migratory insertion reaction is a faster reaction as compared to the oxidative addition reaction over here. So most of the times guys, in the organometallic reactions, the first step most of the time is the oxidative addition, and it is the slowest step, making it the rate determining step. Okay, so this was the explanation of Monsanto acetic acid process. So guys, let's now move on to another question from the December 2019 paper. Okay, so this is also a very good question over here, and this question includes the reactive intermediate carbene. Alright, it includes the formation of, so carbenes are formed by the cleavage of diazo compounds like this. For example, if this is my molecule right over here, I'm just writing it like this. Okay, so one of the bond is going to fall over here and one of the bonds over here. It is going to result into the formation of a carbene like this, and the nitrogen molecule is going to leave. Okay, so definitely guys, here a carbene is going to be formed, and let's quickly make the carbene over here. Although you can just stop the video and do it by yourself as well. Try it out guys, it's a really good question. Okay, so this is the carbene which can be formed. Now what? Now definitely the carbene can either undergo acyl rearrangement, okay, the formation of a ketene, or rather if there is any other possibility, or let's say if there is any other nucleophile which is present in the system, then it can attack over carbene like this directly. Yes, because this is an intramolecular nucleophilic attack, it is really fast. Okay, so I can write the next step like this. Definitely the oxonium ion is going to form. Oxygen has donated its lone pair like this, so definitely there will be a positive charge on oxygen. Alright, and whenever the carbene is attacked by a nucleophile, it is going to get a negative charge on itself. Okay, which will be, this negative charge is now going to take up a proton from the acid. We are having trifluoroacetic acid, which is really acidic, it's a nice acid. So definitely the proton will be taken up, and we are going to get a neutral molecule on this side. What about just a second, what about the oxonium ion? So definitely guys, the oxonium ion will also be hydrolyzed, and very easily, because we are having water in the medium, it is an aqueous acid we are having. So water is going to attack over methyl group, and it is going to release the bonds, and the lone pair will be taken up by oxygen, and this is our final product. So basically what just happened is, okay, so this is our final product. So what just happened is, first of all, the formation of carbene at this carbon over here, alpha to the carbonyl carbon, and then direct nucleophilic attack, because there is a methoxy group which can basically push the electrons from the benzene to attack over this carbene like this, and this is our intermediate formation of a oxonium ion like this. Now in the presence of acid, the negative charge is definitely going to take up a proton like this over here, and there will be the hydrolysis of the oxonium ion, and water is going to take over the methyl group and it forms the ketone like this. Okay, so this forms our dienone system. This forms our dienone system. This is our diene and one, and answer is option number 3. Okay, so I guess that you get the formation of this product. And why not the other one? Why is this not getting formed? Because see, first of all, the number of pi bond is less over here, and even if one of the carbon has to attack, it cannot be this carbon, right? Because the bond movement cannot allow the attack from this carbon, it can only allow the attack from this carbon. And if you draw the mechanism by yourself to make this carbon attack, you will realize that it is not possible to attack from this carbon on the carbene. Okay, alright guys, so these were some questions for today, and I'm going to see you with more questions. Till then, if you want, you can visit my Unacademy profile, and guys, I have already started a lot of questions on the questions as well as topic discussion for the June 2020 examination. Alright, and these are the courses: practice and strategy course, batch course, in which all the 3 educators are taking different subjects. I am taking organics over there, and this is my complete course on organic chemistry. This is my individual course, so I am already we have already completed a lot of topics: the reactive intermediates, then the pericyclic reactions, then reaction mechanisms, stereochemistry. A lot of topics are done, and still more are going on. So from the April, we are going to start our revision and question practice. Revision and question practice, which is basically going to be the MCQs and the previous year questions. So guys, if you want, you can visit the profile. A lot of special classes are also going on. Every month there is a lot of special class and YouTube sessions, so you can also visit for free special classes. And if you want to subscribe, if you are liking the content, then you can use the code JAGRITI for a 10% discount on the subscription packages. Thank you so much guys. I'll see you in the next video. Till then, if you like this, then please give it a thumbs up. Also share with your friends, and also subscribe if you have not yet subscribed. Okay, thank you so much. I'll see you in the next video. Thank you.